bit, or no unitless?
No, I mean, well, I think in our community we renamed it as C-bit because we know that there are many units of many different kinds of numbers. So classical C-bit, qubit, E-bit, and so on.
And that's the same for capacity.
Yeah, so for the capacity, of course, the task is to send a message, and it would be in practice a string of bits from one place to another. But of course, if you want to send quantum information, then we measure in qubits.
And sometimes people say like a bandwidth, the capacity rate, the bandwidth is used, so like a gigabyte per second. So that per second is never considered?
No, so okay, this is something that you can do. I just thought it's a bit easier to convey to have these discretized channel uses. Right, so if you want to talk about bandwidth, this kind of comes about when you have lots of different frequencies. Right, so then you can model a time-dependent modulation, and so then you're looking really at a bunch of channels of this type at the same time, and so that is something that that has been considered. I mean, in the classical case, there's this is the pre-Shannon work, Hearne, Nyquist, and so on. It's the signal processing that you understand. What you have to do is divide information up into those different monochromatic modes. You're completely right to talk about bits per time. You need to do this, but in principle you can do this with the frequencies.
So there is no limit for that gigabyte per second imposed by quantum.
No, by quantum mechanics alone, not. I mean, obviously, if you have a large enough system and large enough power, there is no upper bound.
Yeah.
If you put a power constraint, then it would still depend on the characteristics of the channel, how each of the different bands is affected. But the thing is, each band has some kind of information capacity. And for example, the best case you might have is that you have no power. And this formula here, the low power regime, what it says to you is, if you have no noise at all, then indeed there is no limit, because you can just you proliferate the modes. Like you try to use as many frequencies as possible. And so that per mode you have a very, very small power, because that's better than sticking all the power in one mode. That's very different from Shannon. So in Shannon, you don't see this so much. So in Shannon, you should fill the power kind of more or less evenly among different modes. That's not what's happening. So there's no upper limit in this sense. Yes?
I don't have a clue what the talk was about because I couldn't hear anything. But I heard a question about quantum computing, and I have a quantum computing question. I don't know if you can answer it.
Please.
So anyhow, I was wondering, what's a quantum computer good for versus a classical computer when it comes to questions like relativity versus classical versus like quantum condensed matter versus other kinds of problems you can do in physics? Or what will it be once it becomes that big?
So yeah, I would say one of the principal uses of a quantum computer is what you are implying already, is to simulate physics. And how good and how useful it is depends on the kind of physical system. So the most attractive or the most straightforward one is quantum systems. You want to simulate. Well, that's the first thing. You just want to simulate time evolution of a complex quantum system. That is already something we cannot do in a scalable way on our classical computer architecture. I don't think there is any reason to believe that quantum computers will be any better than a classical computer in simulating I don't know, the Einstein field equations. Because there the limiting factor is just the number of degrees of freedom. You just have to keep track of a lot of numbers. Whereas in the quantum case, there are two kinds of numbers. There are the physical quantities, but then there are also the amplitudes that we have in superpositions. And those, in our computers, we have to represent both of them. Each of them is a variable. Whereas in a quantum computer, the amplitude is kind of taken care of by the quantum state. So this is something that goes back to Richard Feynman, whose picture I didn't have here, despite the fact that he won a Nobel Prize. His main motivation for proposing quantum computers was that this might be a very interesting approach to simulating quantum systems. And both the dynamics and also condensed matter, static or equilibrium properties. That's more or less the picture.
Okay, thanks.
I have a question where you might have to look into your crystal ball. Will we ever have nice formulas for the various capacities of general quantum channels?
I think we'll have rather a quantum computer than a nice formula.
That's up to me.
Yes.
All right. If there are no further questions, let's thank Andreas again.